Our view of the universe is limited by our finite lifespan and the time it takes for light to reach Earth, which hides its majestic form from us. What we consider to be the edge of the universe may not be its edge at all, and most scientists agree that a significant portion of space is hidden beyond what we can see. In the previous episode, we tried to look beyond what humanity had ever seen before. We walked along the very edge of the observable universe, where we could see light on one side and darkness on the other. But is this darkness the edge of the universe, empty space, or some structure located at the center of the universe? Or perhaps not enough time has passed, and the light has not yet reached Earth? Well, as promised in the previous episode, today we will step into this darkness and try to find out what's there. Our past journey ended at the cosmic light horizon, the optical boundary of the visible universe. The view of any observer ends at this cosmic horizon, beyond which the light from distant galaxies has not yet reached Earth. That's why our optical understanding of the universe starts to fade into an all-encompassing veil of darkness. But this veil is not entirely the edge of our universe. The cosmic microwave background, which is ubiquitous relic radiation left over from the Big Bang, is the oldest and most complete signal of the universe, representing the holy grail of modern cosmology. But what if there are several other older signals from earlier periods of the universe's life? Thus, the cosmic microwave background marks the edges of our universe. In turn, allows us to estimate the properties of the space lying beyond its boundaries. In this image, the universe appears smooth and isotropic, with its contents uniformly distributed except for a local degree of randomness. According to the cosmological principle, beyond the cosmic horizon, we find the same galaxy clusters and voids that make up the cosmic web. And if the delay of light did not limit our view of space at a certain distance, the all-encompassing cosmic horizon would begin to disappear, revealing a much larger and more chemically evolved cosmos. The farthest and earliest galaxies, such as GNZ11, HD1, and GLASS Z13, now lie in the depths exceeding 33 billion light-years, having been thrown almost 3 times farther away by cosmic tides than their original distance. Today, these earliest galaxies no longer look like the hotbeds of primary gas and stars, but they are more likely to resemble galaxies in our local group, such as the Milky Way, our neighbor galaxy Andromeda, or the Sculptor Galaxy. Or, they could be giant elliptical galaxies like Messier 87, containing trillions of stars, but having exhausted their star-forming gases. Such galaxies may make up a large portion of what we can find beyond the visible universe. In fact, the question of what lies beyond the visible space is relatively simple. But the more difficult question is, how much is there in total? To answer this question, we need to understand the shape of the universe. Look, for a long time, starting with Aristotle, humanity believed that the universe was a sphere with the Earth at the center. But today we know that neither the Earth, nor the Sun, nor even our galaxy is the center of the universe. Furthermore, from Earth, we see no signs of any barriers. It seems to us that space is full of black holes, where photons of light get stuck. And so we now believe that regardless of the size or shape of the universe, it almost certainly does not have a physical edge. We see that everything in the universe has a spherical shape: stars, planets, and possibly the universe itself also has a spherical shape. The surface of the sphere is finite, but has no boundary. Let's take our planet. Even though it is finite, you can still fly around the Earth infinitely on a plane without encountering any edge. And you will never be able to escape from the Earth on a plane to fly over it, because gravity will bring you back to the starting point. That is why it is believed that the gravity created by the matter of the universe causes the same effect. Such a universe may be infinite or finite in an ever-expanding future. But if the universe is expanding, what is in the point where its expansion began? In trying to answer this question, scientists have sought to establish the geometry of space. But how do you measure, for example, the curvature of the universe? The method of determining curvature consists of studying the boundary of our observable universe. The relic radiation, the remaining radiation from the Big Bang, appears as a screenshot of the entire visible universe when it was only 379,000 years old. Therefore, if curvature exists somewhere in space, it is most likely to be found here. As mentioned earlier, relic radiation is remarkably smooth from all directions. This is due to the gradients of the plane that arose in the plasma of the early universe, which manifested quite consistently throughout space. The question arises, why is the universe so perfectly balanced? All we know is that there are three possible solutions to the problem of the plane. Either the universe is actually flat and therefore likely to extend infinitely, or it is curved, or it may have a theology that hides its true form. The first of these possibilities suggests that the universe is truly flat in all directions and extends to infinity. The idea of an infinite cosmos carries with it terrifying existential possibilities. But it is difficult to imagine how the expanding universe could reach infinity in finite time if it was initially small. The Big Bang theory is suitable for a universe of finite volume, and our universe has other properties that many are trying to find in a finite form. The European Space Agency's Planck satellite confirmed that the level of relic radiation stubbornly shows its constancy and homogeneity. But you will never get this if the universe is unlimited and unscalable. This is actually one of the main arguments in favor of a finite universe. The simplest and most popular example is the universe in the shape of a donut, more commonly known as the toroidal universe. Tori are a fundamental form of geometry that arise in many natural conditions, particularly in magnetic fields. In 1984, two Soviet physicists, Yakov Zeldovich and Alexei Starobinsky, proposed a multifaceted model of the universe, describing its shape as three tori. In other words, a shape where all the edges of the universe are connected. It is precisely how these edges are connected that is key to understanding how the toroidal universe can appear flat, yet be finite and positively curved. Thus, the closed loops of the torus can explain why the relic radiation looks the same everywhere. But the torus universe does not end there, as we must also take into account the flow of time to get to hypertorus. In this case, each void in this torus represents a horizon of the distant past and future, and spacetime flows in one direction. This explains the apparent expansion of the universe simply as spacetime following the geometry of the torus. Emerging from a hole in the horizon of the past, associated with the Big Bang, space rapidly expands at the beginning and then slows down until it reaches the midpoint, where it starts to contract towards the horizon of the future, where it reappears as a Big Bang, giving birth to a cyclic universe. If our universe indeed has the shape of a donut, then perhaps our entire existence is just one turn in an infinite cycle of birth, expansion, and contraction. In recent decades, descriptions of the Big Bang theory have undergone some changes, challenging the idea that the universe grew from a singularity. The unique origin of the universe is simply what scientists arrive at when extrapolating its expansion back to zero time using the structure of general relativity. And while it's quite likely that space and time were born in this environment, the constancy and primordial nature of relic radiation tells us that before the event we call the Big Bang, the universe must have increased in size before this event occurred. And this is the modern answer from cosmologists explaining the size of the universe, its smoothness, and the absence of obvious curvature. Cosmic inflation is a theory that was developed in the late 1970s and early 1980s by Massachusetts Institute of Technology physicist Alan Guth. As a solution to the magnetic monopole problem that hindered the traditional Big Bang model, he and his colleague Henry Tighe proposed that the cooling period could have led the universe to such enormous sizes that its curvature became indistinguishable from the observed universe's flatness. They also speculated that unrestrained expansion was the result of the strong nuclear interaction separating from other fundamental particles in the first seconds after the birth of the universe. It's believed that at the end of inflation, just a few seconds after zero time, the first subatomic matter appeared, which released enormous potential energy and reheated the universe to the level of the Big Bang. After that, the cosmos was flooded with hot plasma, which spread over distances exceeding light horizons. And to this day, many of these fluctuations are burned into relic radiation. These fluctuations are one of the remarkable observational evidence of cosmic inflation. The same process that seeded the universe with density through inflation should have released gravity and a series of gravitational waves, which still propagate throughout the universe. In the center of the Big Bang, a void was supposed to form, but as we know, sacred places are never empty, and the gravity that was born here attracted some of the matter and photons of light from the Big Bang, just as supermassive black holes in the centers of galaxies attract the photons and matter of the galaxy. We always talk about the Big Bang, but few researchers think and talk about what remained at the epicenter of the Big Bang. And now, an international team of astronomers who discovered the farthest galaxies suggests that there may be a huge gravitational structure beyond the visible universe that formed at the moment of the universe's birth. This structure attracted some of the matter released by the Big Bang back. The second part of the matter formed an accretion disk, and the third part began to rotate around this gravitational center, where stars and galaxies were formed thanks to that very gravity. That is why when we look into space, we see darkness. But in reality, it is not darkness. It is primordial darkness. It is a huge universal black hole that rotates the entire universe. This is where all the galactic clusters are directed, just as stars in a galaxy are directed and rotate around a supermassive black hole, and planets rotate around stars, each with its own orbit. Orbits of planets, as we know, can be elongated, causing some planets to move away from each other and from the star, just like galaxies. Some, according to their orbits, move away from us, and we think that the universe is expanding. Others, on the contrary, approach and collide. But if we look at galaxy clusters as a whole, it becomes evident that they are all directed in one direction and moving in the same direction, connected by the threads of the recently discovered dark flow. However, this hypothesis is still awaiting confirmation from the James Webb Space Telescope. Let's hope that it will confirm or refute it soon. That's all from me today. Leave your comments, give likes, and also take care of yourself and your loved ones. Thanks to everyone who supported me. All the best to you, dear friends. And until new, even more interesting space meetings.